a lot of this is going to be rehashed from the notes video that you guys watched on Monday. But we get into logs. This is something that can get a little tricky for some students, so I figured there's no harm in going over this again. If you feel like you totally got this, just think of this as an opportunity to just to review a little bit and strengthen your understanding. So here's the big thing I hope you got out of our notes, and that is what is a log? A log is what? Logs are, you guys remember? Exponents. Logs are exponents. And that's the key to success here, is to remember that logs are exponents. And so because of that, when we get into log properties, if you know your exponent properties and you can relate those, that's going to make it easier for you to learn and apply those. Let me show you something really quick that my Algebra 1 students are struggling with right now. And I want you to think about the similarities between this and what you're learning with logs. Okay, so here's something my Algebra 1 students are pretty good at right now. If I tell them to take 2 and put an exponent of 3 on it, they can tell me that the answer is 8. A lot of times they want to say 6, but they know if they work it out, it's 2 times 2 times 2, and that's 8, right? What's trickier for them is if I give them the cube root of 8. And we know the answer to that. It's what? It's 2. It's really the same problem, isn't it? Like, just sort of in a different format. This is in an exponential format, and this is in a root format. You guys have seen cube roots and square roots enough that you understand them really well, but my Algebra 1 students are it's kind of mysterious to them. Like, they'll ask me a question like, hey, Mr. Height, when we see the cube root of 125, what is it they're asking me to do? How would you explain that to a kid? If an Algebra 1 student came up to you right now and was like, what is the cube root? What is it? What is it asking me to do? What would you tell them? Yeah, what do you think? Yeah. So the basic idea is you're trying to find something that multiplies by itself 3 times, and we want the answer to come out to be 125, right? Or in other words, can you find me some number I can put an exponent of 3 on to equal 125? That number right there is going to be the same as this number out here. Agreed? So if I can get them to understand the relationship between this type of equation, which they have no trouble with, and this type of equation, then eventually, like, you kind of start, you see the connections between them, and you don't have to think too hard about it. Now when you guys see a cube root or a 4th root, you understand intuitively what we're asking for. The same thing is going to happen for you with logs eventually. Logs are one of those things that, like, we introduce it, and it kind of looks weird, and they seem mysterious at first, but it's really just a different way to ask the same kind of question that you're familiar with already. Let me get my battery plugged in here, and we'll continue. So why don't you guys do this for me while I'm getting this plugged in? Could you go ahead and fill in the blanks in this column here in our notes? This is something that we're familiar with. We are used to exponential style equations, and you guys know what they mean. So if you haven't already, go ahead and fill those in. Just that first column. Are we feeling pretty confident about this? 9 is 3 to the second. 16 is 2 to the what power? 1 over 25, that's 5 to the 25 would be 5 squared, but it's 1 over, so -2, good. 10,000, count the zeros there. How many zeros? So that's 10 to the 4th. This one, you got to know some exponent properties for this. What do we do with this x and this 5? We're multiplying them together here. What happens when we what happens to exponents when we multiply? We add them. This would be x plus 5. These equations over here are analogous to the ones on the left. They're just being asked in a different format. So once you get used to the format, you're going to see that it's really asking the same thing. When I ask you to find log base 3 of x, I'm asking you, what's the exponent I could put on a base of 3 to make it equal to 9? And the answer is 2. Here, what's the exponent that I could put on a base of 2 to make it equal to 16? The answer is 4. All of these exponents that we came up with are the answers to these questions because these are logs, and logs are what again? Logs are exponents. So I'm going to skip this this side over here because we're going to practice a whole bunch of these on the flip side of this page. But let's just kind of go through and sort of put this in language. So what I want you to start doing when you see something like log base 2 of 8, I want you thinking in your mind, what I'm really asking you is the exponent that I would put onto a base of 2 to make it equal to 8. And what exponent would you put onto a 2 to make it equal to 8? 2 to the third power is 8. So the log base 2 of 8 is 3 because that's the exponent I put on a 2 to make it equal to 8. Log base 5 of 125. I want you thinking in your head, that's the exponent I put on a 5 to make it equal to 125. And what is that exponent? 3 again. 5 to the third is 125, so log base 5 of 125 is 3. Log base 7 of 1/7, I want you thinking to yourself, what's the exponent I put onto that base of 7 to make it equal to 1 over 7? And the answer is negative 1. All right, so why don't you guys practice this? Did you get from your notes last time these special logs? Are you aware that if they don't put a base on the log that you're to assume it's log base 10? A lot of my students will actually write that base in. I think that's a smart move. If it helps you, go ahead and do that. If not, don't worry about it. And you also know if you see ln, ln stands for what? Natural log. Why did they not call it NL then? Because it was a French person that I'm pretty sure. And how do adjectives work in French? They're backwards. Logarithm naturel. I think it was a French person. I could be wrong about that. Anyways, but that goes with a log base E. Since it's so common, you know, they did that typical thing that mathematicians do and just shorten it as much as possible. So ln is an implied base of E. So see what you can do there. We'll go over answers here in a moment and give you a chance to ask questions. I'd love to talk about any of these. Do you guys have any that you wanna go over? Are these last three kind of making sense to you? Like when they say the log base 10 of 10 to the 15th, if we kind of think about how do we ask that question, kind of using the language we were using up here, the question is, what exponent could I put onto a base of 10 to make it equal to 10 to the 15th? And that question's kind of trivial, right? Obviously, it's 15. So these last three kind of go with the notes that are here, and I don't know that this was in the notes that I left for you guys from Monday. But since logs and exponentials are inverses of one another, if you end up either with an exponential inside of a log or a log inside of an exponential, as long as the bases match, those two things will cancel each other out. The same way that a square and a square root cancel each other out, the same way that division and multiplication cancel each other out. They're inverses of one another, but the bases must match to make this work. So the top three examples here down at the bottom are pretty straightforward because we've got an exponential base 5, log base 5. Those would cancel. We're just going to have that 3 left over. Same thing in this situation. We've got an exponential base e, and then ln has an implied base of e in it also, so those would cancel when we get 7.2. The ones down at the bottom are a little bit trickier. Let's talk about these. Again, are there any from 1 to 17 that you'd like to go over, aside from 10 or 11, which don't exist? All right, let's do these couple at the bottom. So these ones are a little bit trickier because we got to use our rules for exponents here, kind of in reverse. And again, my my assumption is that you guys are masters of exponents. That between Algebra 1 and Algebra 2, you've mastered exponents. And if that's not the case, then you need to get yourself there either with my help or on your own. Just let me know if you need some assistance. So I assume that you know, when do we add exponents? We add exponents when we're doing what? When we're multiplying. If I had two things that had the same base with exponents on them, we would add those exponents. The exponents I'd be adding here are the 2 and the log base 5 of 3. So I could rewrite that as two separate exponentials. Why would I ever do that? Well, I know what 5 squared is. It's 25. And now that this is separate, I have a base and or a base that matches my exponential and my log. Those are going to cancel. That's just going to turn into a 3. So my answer there is going to be 75. For the second one, I really, really, really want to cancel this base of 2 and this base of 4, but they don't match. However, I've got a 2. I'm looking at this as a 2 being multiplied by a log base 4 of 3. In what situation do we multiply exponents? Yeah, when we've got a power to a power. Usually we write it with a parentheses. So if I had 2 squared with a log base 4 of 3 on the outside, that would be where I'd multiply the 2 times the log base 4 of 3, and I get 2 log base 4 of 3. And if I wrote it that way, I could rewrite that 2 as a 4, which now matches the base on my log. So now they would cancel and give me my final answer of 3. This last one, I look at it and I see 2 exponents that are being subtracted. In what situation would we ever subtract 2 exponents? When we're dividing. That would be 10 to the log base 10 of x over 10 to the first. We know what those two things are. The bases here match, so that would just be x on top, and 10 to the first is just 10, so x over 10. Bless you. Anything on that front side that you guys would like to go over? Oh, thank you. Nice. Thank you, thank you. That looks great. Anything else on that front side you guys would like to go over? All right, flip it over. Okay. Who here has heard of the circle of success? You guys remember that from last year? Circle of success. I want to show you this, okay? I don't want you to write it down. I want to show it to you. Because some people might call it something else. So if I had, let me match here, the log base b, you don't need to write this down. In fact, I prefer that you do not write this down. All right. If I wanted to change this into exponential form, how do we do that? So I had a student who made this really cool story up about this and really helped a lot of people understand this. And I think this is great for like an Algebra 2 level. Pre-calc, we need to move beyond this, but let me show you just so we're all on equal footing here. So how many people have learned that you can just take this base over here and move it over to the other side? Have you seen this before? Yep. So her story involved, so there was a base here, and it's going to go to the other side of the river. The equal sign was the river. And it's going to pop this c up in the air. C is going to become an exponent. And for some reason, the base was holding up the log, so the log rolls down the hill, and the a is all that's left over. So what would happen is base comes over here, pops the c up in the air, and then the log rolls away, and all you have is the a there. Have you seen something like that before? And there's a, maybe not with that same story, but then you can do the same thing in reverse, right? The base here moves the other side, and it becomes a base on the log, and the log comes back. I don't know how that, I can't remember how that way worked. Okay, now this is great if you're just learning logs and all you're worried about is trying to get right answers. Okay, if you are now in an upper level math course where you're expected to actually understand what's going on, this kind of falls apart because there's not a whole lot of math going on here. We don't just move bases from one side of the equation to the other side. So if you know this, I don't want you to forget it, but I want you to put it to the back of your mind. Okay, I'm going to challenge you. This will get you right answers, but it's not going to help you understand, okay? And it's not going to get you correct answers on like some of the multiple choice questions or maybe the last question on the test or a lot of the interesting things you're going to be dealing with next year in calc. So I'm going to give you kind of a different way to look at this instead. And I'm going to challenge you to try and really view this from a lens of understanding how logs work rather than just kind of moving stuff around in an equation. Are we okay? So let me show you this. When you look at this equation, can you identify what the base in this equation is? What is the base in this equation? B is the base. So label that with the base. B is the base. And in that equation on the left, can you identify what is the exponent? In this equation, what is the exponent? C is the exponent. How do we know that C is the exponent? Because a log is an exponent, right? Now in this equation, notice that B is also the base and C is also the exponent. Now if you can keep track of where the base and the exponent are supposed to be in each of these things, then you can just use that to translate between them. Rather than trying to move stuff across an equal sign, I want you to try and understand that you're really looking at the same stuff, a base and an exponent, just kind of in a different format. So let me show you how this works here with this first example. Look at this equation and tell me what's the base in this equation. Copy that down over here someplace. It doesn't matter. I'm going to put it on this side. 2 is the base. And tell me what's the exponent in this equation. The log is the exponent. So 16 is the exponent. Put a 16 on that 2. And the thing that's left over is the x. So that's going to be equal to x. That's the exponential equation here. Look at this second one. Tell me what's the base. Base is 5. I'm going to put the base over here this time. I don't know why, because I feel like it. What's the exponent? X is the exponent. Remember, the log is the exponent. 42 is the thing left over, so it's over there. If you want to put your 5x on the other side, that's fine. It doesn't really matter. The important thing is that the base and the exponent are attached to one another, right? So look at this next one. Now the base is not written here, but what is the base? It's an implied 10. So put that base in your equation someplace. What's my exponent? Remember, the log is the exponent. The exponent is 3. And x is what's left over. See if you can do those last couple for me. Don't think about moving a base from one side to the other. Ask yourself, what is the base? What is the exponent? Get them in the right spots. What is the base? What is the exponent? What is the base? What is the exponent? Remember, the log is the exponent. Now, if you've got your equations flipped around from mine, that's okay. It doesn't matter. Doing this the opposite direction, I like to set up I'm going to set up all my equations first. I like to have my logs on the left. I don't know why. Doesn't really matter. So we're just going to ask the same questions. What's the base? What's the exponent? We'll make sure they go in the right spot. So what is the base in this equation? The base is 6. So put that on your log. And what's the exponent? The exponent is x. Now where's the exponent go here? The log is the exponent. So the exponent goes over here. 1,000 is the remaining piece. What's the base? The base is 2. What's the exponent? The exponent is x. What's left over? That's pi. See if you can fill out the rest of those.
When you multiply it, like on the last
Mm-hmm.
one, the 4 becomes an exponent within the logarithmic.
So we haven't gone over those properties yet. But yes. Yeah, let me catch up to you here. What's the base? What's the exponent? So I would probably rewrite this as ln in common logs. So there's a number of ways to deal with this last one. What I'm going to suggest is, the way I'm going to deal with this is I'm going to get this so it's a single base on the left-hand side. A couple ways. I could divide both sides by 4. That's totally legal. Yep. What I'm going to do instead, though, is I see this base of 2. I'm going to rewrite 4 as 2 squared. Now I've got 2 bases that match. And I can now combine these together into a single base. What am I going to do with my exponents? Add them. So 2 to the 2 plus 3x equals 11. That's how I'd start that. So what's my base? My base is 2. What's my exponent? My exponent is 2 plus 3x, and that 11 is going to be left over inside.
Instead of putting the 2 there, you can put the 4 over the 11.
Yeah, so another way to deal with this would have been to divide by 4 on both sides. So that would have gotten us 2 to the 3x equals 11 over 4. And then my base would have been 2, so log base 2. My exponent is 3x, and this would have been an 11 over 4 here. That would have been another way I could have done it. Question? Can I just multiply the 2 by 4 and call that 8 to the 3x? That's a good question. Now, technically, no, because technically this 4 has its own exponent. It's an exponent of 1. So no, we cannot. We can't combine the bases together unless they match. But we can do clever things to make them match. And I want you to remember that because we're going to learn a way to make bases match for logs here in a bit too. Great question. Question was, can I just combine these together and call that 8 to the 3x? And the answer is no. That's a very common mistake, though. Other questions before we move on? We are going to do this next part really quickly. What's the relationship between logs and exponential functions? I'm going to tell you right now they are inverses. Logs and exponential functions are inverses. What happens to x and y values when you do an inverse? They flip. So if negative 1 comma 1/2 was on our original function, then the inverse would have 1/2 comma negative 1. 0 comma 1 becomes 1 comma 0. 1 comma 2 becomes 2 comma 1. This horizontal asymptote at y equals 0 is going to become a vertical asymptote at x equals 0. All the x's become y's, all the y's become x's. So originally we had a horizontal asymptote. We're now going to have a vertical asymptote. And I'm just going to graph these points. 1/2 comma negative 1. 1 comma 0, 2 comma 1. And this is the general shape for a logarithmic function. Yes, please do. What's the question? Guys, what are you taking pictures for? Okay. Thank you. Yeah. I'm just making sure that it's like an official school thing and you're not just being creepy. All right. Ask that question again. No, I want to hear it. If they mean basically the same thing, then why is it an inverse? That's a good question. So like some other inverses are like square and square roots. So you can write an equation with a square that means the same thing as a square root. We kind of did this a second ago. These two equations mean the same thing. But a cube is not the same thing as a cube root. It's kind of asking the opposite question. When I ask you to cube something, I'm asking you to multiply something by itself 3 times. When I ask you to cube root it, I'm asking you to tell me what do I multiply by itself 3 times. So it's asking kind of the opposite question. But the equations mean the same thing. They have the same numbers in them. They encompass the same concept. So other examples of inverses are like adding 2 and subtracting 2. Those two mean 2 different things, right? But they're related to one another, right? One of them undoes the other, is another way to think of it. So when we were doing our canceling on the other side, this is a really good question. I'm glad that you asked this. When we were doing our canceling over here, right? When we were canceling a natural log with base e and an exponential base e, the reason that those things canceled are because they're inverses, right? Inverses will cancel one another. One undoes the other. So, great question. Thank you. All right, let's talk about analysis here. What happens to our domain and range for inverses? They just flip. So the domain was all real numbers. That's going to become the range now. So the range is all real numbers, and that makes sense. That's what I'm seeing here. The y values go from negative infinity to infinity. The range was 0 to infinity. Now that's our x values. That's our domain. So our domain is 0 to infinity. We got an intercept. There's a single intercept. It used to be 0, 1. Now it's 1, 0. It's right here. We used to have a horizontal asymptote at y equals 0. Now we have a vertical asymptote at x equals 0. Tell me about the log function. Is it increasing still? Yeah. Is it increasing for all real numbers? No, because the graph doesn't cover all real numbers in the x direction, does it? It only increases from 0 to infinity. So it increases over the whole domain, which is 0 to infinity. Are we still continuous? Yep. Still bounded below? No, we're not bounded at all. Still no symmetry. And then this next part's kind of interesting, end behavior. Let's do the easy part first, the right-hand end behavior. Is the right-hand end behavior going up, down, or leveling off? It's going up, so it's going to go up forever and ever. So the limit as x goes way off to the right towards positive infinity, the y values just keep getting bigger and bigger and bigger. The interesting thing is that they get bigger and bigger, but at a super slow rate. So when it almost looks like there could be a horizontal asymptote on these, but if you keep going out far enough, it will cross any line that you think could be the horizontal asymptote. You just might have to go super far to get there. It may look like it has a horizontal asymptote, but you will always go past that horizontal asymptote if you go far enough out to the right. What about the end behavior on the left? It's kind of a trick question. Does this graph have x values that approach negative infinity? No, it goes to 0, and it actually doesn't go past 0. It doesn't touch 0. So that is the end behavior. We can't talk about an end behavior on the left because the graph doesn't go off towards negative infinity, which is kind of weird. We know one other parent function, at least, that does not have an end behavior on the left. What other one can you think of? Square root function does not have end behavior on the left either. So that can happen. So, We just wouldn't have it. We're used to having n behavior on the left and right, but not all functions do. This one doesn't. So we're just, when we ask for n behavior, there's only one side that has n behavior. So we don't talk about n behavior on the left because there is none.
Not even like the other way, where it's like limit as x approaches 0.
So that wouldn't be n behavior. That would be the behavior around the asymptote. So we could do that. This is a good question. I'm gonna write this down. So if we talked about our behavior on the asymptote, this is not n behavior. It would be the limit as x approaches, where is that vertical asymptote happening? 0. And we can only talk about it approaching 0 from one side, from the right or from the left? From the right of f of x is equal to what? Negative infinity. So we can talk about half of the behavior around that vertical asymptote, but not the other half. That's cool. Thanks for asking that. I hadn't thought about that. Yes? Wow. Excuse yourself. That was good. That had some nice tone. Yeah. Those two graphs combined look like a reciprocal. They kind of do. Yeah. Yeah, I like that. Again, this kind of will look like it has a vertical asymptote, but it doesn't, right? And a reciprocal would need that. But yes, if you put them together, they do kind of resemble a reciprocal function. Awesome. All right, we're not going to go over this, nor an example of this, but I totally reserve the right to put this on a test. If I ask you to describe the functions, it would take log base 4 of x to this. Would you be able to do that right now? Let's run through it. What's that negative going to do? Reflection over the x-axis. 2 on the outside is a vertical stretch by 2. X minus 1, that's a shift to the right by 1. Plus 3 is a shift up by 3. Yep. If I asked you to tabulate and graph this by hand, what would you use for your parent points? Let me show you what you would use for your parent points. You would use -1, 0, and 1, but we're actually going to put those in the y values this time. -1, 0, and 1. Yep, and this would be 1/4 and 1 and 4. Because it's a base of 4. This is a base of 4. Okay. Oh, and you'd want to graph also the vertical asymptote x equals 0. You'd want to tabulate that as well, because that's going to end up shifting. When we shift to the right by 1, this is going to shift that to the right by 1 also. It'll become x equals 1. All right. Not going over it, but totally fair game for a test. We're moving on to properties of logs. Let me start this over again.